Hello students, welcome to Sciacademy. Hope you all are good and doing well and learning the physics very well. Students, in this video lecture, we will be learning about the diffraction, law of refraction, Snell's law, and total internal reflection, and the important properties of refraction of light. So students, let's start the video lecture. If you like this video, please press the like button and share with your friends so that they can also learn about this lecture. And if you are watching for the first time, please subscribe the Sai Academy channel. When a beam of light encounters transparent medium, a part of light gets reflected back into the first medium while the rest enters the second medium. A ray of light represents a beam, the direction of propagation of an obliquely incident ray of light that enters the other medium changes at the interface of the two media. That is, when a ray of light incident on a interface of the two media, then its direction changes. Some part of this incident ray gets reflected into the first medium, and some part of this incident ray gets refracted into the second medium at the interface of the two media. And this phenomenon is called refraction of light. Snell experimentally observed some facts about this refraction of light, and he summarized those things into statements. The first statement is the incident ray, the diffracted ray, and the normal to the interface at the point of incidence all lie in the same plane. So you can see this is the plane, and in this plane the incident ray, the reflected ray, and the refracted ray and normal all lie in the same plane. And the second statement is the ratio of the sine of the angle of incidence to the sine of angle of refraction is always a constant, and this constant is known as the refractive index. So, the ratio of the sine of angle of incidence to the sine of the angle of refraction is equal to the constant, and this is known as the refractive index of the second medium with respect to the first medium. So, here it is n21. This means that this is the refractive index of the second medium with respect to the first medium. If you want to write the refractive index of the first medium with respect to the second medium, then notation changes, and that will be written as n12. That means n21 is equal to 1 by n12. So these two will be inversely proportional to each other. And these two statements is known as the Snell's law of refraction. It is important to note that the refractive index is a characteristic of the pair of media, and it is independent of the angle of incidence. It doesn't depend on the angle of incidence, but yes, it depends on the wavelength of the light which is incident on the interface of the two media. Now, if the refractive index of the medium 2 with respect to the medium 1 is greater than 1, then in that case angle of incidence is greater than angle of refraction. That is, medium 2 is said to be optically denser than the medium 1. And the other hand, if the refractive index of medium 2 with respect to medium 1 is less than 1, then in that case angle of incidence will be less than angle of refraction. That means in that case the medium 2 will be rarer than the medium 1, and in that case refracted ray bends away from the normal. Now we will understand about the optical density. What is the meaning of denser medium optically? So, students, optical density should not be confused with the mass density. It is different thing. Mass density, it is defined as the mass per unit volume. But the optical density is the ratio of the speed of light in two media. For example, turpentine and water. Mass density of the turpentine is less than that of the water, but its optical density is higher. So it means that a medium may be having the high mass density, but it may be having the low optical density, or vice versa. So, students, we define the refractive index as the ratio of speed of light in free space to that in a given medium V. So, refractive index basically is the N is equal to C by V, and it is also denoted as mu. So in some textbooks you can get this as a mu. Here it is written as in terms of N. Now we'll learn about the some important properties of the refractive index. So first point is that it is a scalar quantity and has no unit. So it is a scalar as well as dimensionless quantity. Second important point is if epsilon naught and mu naught are electric permittivity and magnetic permeability respectively of free space, then according to electromagnetic theory, the speed of light can be written as c is equal to 1 by square root mu naught epsilon naught. So students, please mark it. This is very important fact. It is also asked in some important competitive examination. The relationship between the speed of light and the permittivity and magnetic permeability of the free space. If the epsilon and mu is the permittivity and permeability of any medium, then the velocity of light in that medium is given by 1 by square root epsilon mu. So, if the light passes through any medium having the electric permittivity epsilon and magnetic permeability mu, then the speed of light in that medium will be given by 1 by square root epsilon mu. Therefore, we can define the refractive index n as c by v, and that is equal to square root epsilon mu divided by epsilon naught mu naught, and that is equal to square root epsilon r mu r, where epsilon r and mu r are the relative electric permittivity and relative magnetic permeability of the medium. Next point. Now we will learn about the lateral shift of a ray refracted through a parallel sided slab. So, so, you can see in this figure 9.9, a ray incident at angle I1 from medium air to the interface between air and glass here, and after refraction through the glass, it refracted at angle R1, and then it propagated inside the glass or slab, and then it again refracted out from the denser media into the first medium. So you can see here that angle of incidence I1 is equal to angle of refraction R2. Therefore, in this case, the refraction takes place at two interfaces, here as well as here, and the emergent ray becomes parallel to the incident ray. So this ray is parallel to this ray, and there is no deviation, but it does suffer lateral displacement with respect to the incident ray, and this is known as the lateral shift of a ray. Next important point is, in a vacuum, the speed of light for all wavelengths is maximum. Then in that case, refractive index n is equal to c by v becomes c by c is equal to 1. Therefore, all the wavelengths will have the same refractive index in free space, and that is equal to minimum 1. For a given light, denser is the medium, lesser will be the speed of light, and so greater will be the refractive index. That is, if velocity of light in glass is v glass, then it will be lesser than the velocity of light in water. Hence, refractive index of the glass will be greater than the refractive index of water. So, greater is the velocity, lesser is the refractive index, and vice versa. Therefore, for a given light, diffractive index depends on the nature of the medium. For a given medium, the speed of light of different wavelength is different, and that is V is directly proportional to the wavelength of the light, and refractive index is equal to C by V implies that refractive index is inversely proportional to wavelength of the light, as velocity can be written as frequency into wavelength. That is, greater the wavelength of light, lesser will be the refractive index. That is, in this case, wavelength of the R is greater than wavelength of the blue, and therefore refractive index for red light will be lesser than refractive index for blue light. Now we will understand about the apparent depth and normal shift phenomena. So consider this figure 9.10. So in this figure, this is denser medium. Suppose this is water and this is rare medium. Suppose this is air. So refractive index of air mu2 and refractive index of water mu1. So this is denser medium and this is rare medium. Suppose this is point B and angle of incidence is I. This is also I, and this is angle of refraction, and that is equal to this angle R. So we want to understand about the apparent depth and normal shift. So if a point object O in one medium is observed from other medium, and since the boundary is plane, then from Snell's law we have mu1 sine I is equal to mu2 sine R, where mu1 is the refractive index of the denser medium and mu2 is the refractive index of the rare medium. Therefore, if the rays OA and OB are close enough to reach the observer's eye, then sin I is equal to tan I is equal to AB by AO, and sin R is equal to tan R is equal to AB by O prime A. So then the Snell's law becomes mu1 sine mu1 value of sine I, that is AB divided by AO, is equal to mu2 AB divided by O prime A, and that gives OA that gives O prime A divided by OA is equal to mu2 by mu1. This gives OA divided by O prime A is equal to mu1 by mu2. Now there are two possibilities. First, if mu1 is greater than mu2, that is object in a denser medium is seen from a rarer medium, then in that case OA will be greater than O prime A. That is, the image of object will appear at a lesser distance. This is why an underwater object like stone or fish appears to be at lesser depth than in reality. The distance between object and its image is called the normal shift. So this is called the normal shift. OA minus O prime A. This is called the normal shift. And this normal shift can further be given by OA minus O prime A is equal to OA minus OA divided by mu is equal to OA into 1 minus 1 by mu, where mu is equal to mu1 by mu2, mu denser by mu rare. So we see that the normal shift is given by original depth into 1 minus 1 by mu. Now we will take the second case. What if mu1 is less than mu2? Is if the object in a rare medium is seen from a denser medium. Object in rarer medium is from seen from denser medium. Then in this case mu1 divided by mu2, that is mu rare by mu denser is less than 1, and therefore O prime A will be greater than OA. That means the image of the object will appear to be at a greater distance. This is why a high flying object like bird or aeroplane appears to be higher than in reality, and normal shift in this situation will be given by O prime A minus OA is equal to mu minus 1 into OA. Students, similarly, we can also know that the refraction of light through the atmosphere is responsible for many interesting phenomena, such as sun is visible a little before the actual sunrise and until a little after the actual sunset due to the refraction of light through the atmosphere. By actual sunrise, we mean the actual crossing of the horizon by the sun. You can see in this figure, here is the observer and this is the horizon. So if sun in the morning is here, because of this refraction of light coming from the sun, it appears to sunrise early before reaching above the horizon. Similarly, it stays more time after the sun is set, that is around 2 minutes. Similarly, the apparent flattening or oval shape of the sun at sunset and sunrise is also due to the refraction of the light in the atmosphere. Now we will study about the total internal reflection. Under the total internal reflection, when light travels from an optically denser medium to a rare medium at the interface, it is partly reflected back into the same medium and partly refracted to the second medium. This reflection is called the internal reflection. You can see in this figure, here light is moving from the denser medium to the interface with the rarer medium, and after reflection it coming in this direction, and it is also some part of this light is also refracted in this way. So this reflection in the same medium from where the light is starting moving is called the internal reflection. What if total light is getting reflected without any refraction? That is called the total internal reflection. So, when a ray of light enters from a denser medium to a rarer medium, it bends away from the normal. For example, the ray AO1B in figure 9.12, the incident ray A1 is partially reflected O1C and partially transmitted O1B, that is refracted. The angle of refraction is larger than the angle of incidence as the light is coming from the denser medium to rarer medium. As the angle of incidence increases, so does the angle of refraction. Till for the ray AO3, the angle of refraction is pi by 2. The refracted ray is bent so much away from the normal that it grazes the surface at the interface between the two media. This is shown by the ray AO3D in figure 9.12. If the angle of incidence is increased still further, the refraction is not possible and the incident ray is totally reflected inside the same medium. So here, after each reflection, the angle of incidence is increasing, and for a particular angle of incidence, the angle of refraction becomes pi by 2. That means it grazes this interface, and after this, when angle of incidence is little more than the previous one, the light gets totally reflected within the same medium instead of getting refracted. So here there is no refraction, and that is called the total internal reflection. When light gets reflected by a surface, normally some fraction of it gets transmitted. The reflected ray, therefore, is always less intense than the incident ray. However smooth the reflecting surface may be. In total internal reflection, on the other hand, no transmission of light takes place. All of the light reflected back into the same medium. The angle of incidence corresponding to angle of refraction pi by 2 is called the critical angle for the given pair of the medium. That is that angle of incidence for which the angle of refraction becomes 90 degree, that is called the critical angle for a given pair of the medium, that is medium, denser and rarer. We see from the Snell's law that if the relative refractive index of the refractive medium is less than 1, then since the maximum value of sin r is unity, there is an upper limit to the value of sin I for which the law can be satisfied. That is, for I is equal to IC, such that sin IC is equal to n to 1, refractive index of medium 2 with respect to medium 1. For values of I larger than IC, Snell's law of refraction cannot be satisfied. Hence, no refraction is possible. So, that means only the angle of incidence equal to critical angle is possible, not more than the critical angle is possible. The refractive index of the denser medium 1 with respect to the rarer medium 2 will be given by n12 is equal to 1 by n21 is equal to 1 by sin IC. Some typical critical angles you can see in the table 9.1. So for the water, it is refractive index is 1.33 and critical angle is 48.75. So minimum critical angle is for the diamond as the refractive index for the diamond is higher, that is 2.42. You can also see that higher the refractive index, lesser is the critical angle. That's why in diamond total internal reflection phenomena is the possibility. Students, there are some important applications of the total internal reflection in nature, and we will see one by one. Mirage. So, students, you might have heard about the mirage in the desert. In the figure, you can see that on the hot summer days, the air near the ground becomes hotter than the air at the higher levels. The refractive index of air increases with its density. The hotter air is less dense and has a smaller refractive index than the cooler air. So, the refractive index at the higher levels has the small refractive indices. If the air currents are small, that is no circulation of air, that is the air is still, the optical density at different layers of air increases with height. As a result, light from a tall object such as tree passes through a medium whose refractive index decreases towards the ground. Thus, a ray of light from an object successfully bends away from the normal and undergoes a total internal reflection. If the angle of incidence for the air near the ground exceeds the critical angle, you can see in the 9.14 figure B, to a distant observer, the light appears to be coming from somewhere below the ground. The observer naturally assumes that light is being reflected from the ground. That means the observer becomes confused about the pool of water near the tall object. Such inverted image of the distant tall object cause an optical illusion to the observer. This phenomenon is called mirage. This type of mirage is especially common in the hot deserts. Some of you might have noticed that while moving in a bus or a car during a hot summer day, a distant patch of road, especially on a highway, appears to be wet. Because of the hot summer, the road becomes hotter and having the refractive index lower than at higher level. But if you don't find any evidence of wetness when you reach that spot, this is also due to the mirage phenomena. So you can see here that for the observer, light is coming, for the observer, light appears to come from here, and that's why he or she assumes that there is some water body. Similarly, the total internal reflection phenomena happens in the case of diamond. Diamonds are known for their spectacular brilliance. This brilliance is mainly due to the total internal reflection of light inside them. The critical angle for the diamond-air interface is almost equal to 24.4 degree. That is very small. Therefore, once light enters a diamond, it is very likely to undergo total internal reflection inside it. Diamonds found in nature rarely exhibit the brilliance for which they are known. It is the technical skill of the diamond cutter which makes diamonds to sparkle so brilliantly. By cutting the diamond suitably, multiple total internal reflections can be made to occur. That means naturally occurring diamonds by itself has the lesser possibility of the total internal reflection. The diamond cutter makes the, by his technical skill giving the proper shape to the diamond so that internal reflection phenomena can be made to happen. In the case of prism designed to be bent light by 90 degree or by 180 degree make use of total internal reflection. Such a prism is also used to invert images without changing their size. In the first two cases, figure 9.15a and 15b, we can see that critical angle IC for the material of the prism must be less than 45 degree. And we see from the table 9.1 that this is true for both ground glass and dense flint glass. So by using the crown glass and flint glass, we can make the prism so that the total internal reflection may happen. In the case of optical fiber, total internal reflection also happens. And you know that optical fibers are extensively used for transmitting audio and video signals through long distances, very less attenuation of the signals. Optical fibers too make use of the phenomena of the total internal reflection. Optical fibers are fabricated with high quality composite glass quartz fibers. Each fiber consists of a core and cladding. So this is the core area and this is the outer area is the cladding. The refractive index of the material of the core is higher than that of the cladding. Because of this interface, the light after each reflection getting into inside and therefore it always propagated inside the fiber. When a signal in the form of light is directed at one end of the fiber at a suitable angle, it undergoes repeated total internal reflection along the length of the fiber and finally comes out at the other end. Since light undergoes total internal reflection at each stage, there is no appreciable loss in the intensity of the light signal because there is no transmission of the light in case of the total internal reflection. Optical fibers are fabricated such that light reflected at one side of the inner surface strike the other at an angle larger than the critical angle, hence always propagating further. Even if the fiber is bent, light can easily travel along its length. Thus, an optical fiber can be used to act as an optical pipe. A bundle of optical fibers can be put to several uses. Optical fibers are extensively used for transmitting and receiving electrical signals, which are converted to light by suitable transducers. Obviously, optical fibers can also be used for transmission of optical signals. For example, these are used as light pipe to facilitate visual examination of internal organs like esophagus, stomach, and intestine. Therefore, optical fibers are very useful in the medical diagnosis also. You might have seen a commonly available decorative lamp with fine plastic fibers with their free end forming a fountain-like structure. The other end of the fiber is fixed over an electric lamp. When the lamp is switched on, the light travels from the bottom of each fiber and appears at the tip of its free end as a dot of the light. These fibers in such a decorative lamps are optical fibers. The main requirement in fabricating optical fibers is that there should be very little absorption of light as it travels for long distances inside them. This has been achieved by purification and special preparation of the material such as quartz. Quartz are extensively used in the manufacturing of the optical fibers. In silica glass fiber, it is possible to transmit more than 95% of the light over a fiber length of 1 kilometer. So, students, this is for now. Hope you learnt through this video lecture about the refraction of the light and its important physical properties and about the total internal reflection with important examples and its applications. Hope you enjoyed this video lecture and would like to share with your friends so that they can also learn about this topic. So please share this video lecture with your friends and like the video. And if you are watching this Sai Academy channel for the first time, please subscribe the channel Sai Academy. Your likes and your shares motivate us to provide you the knowledgeable video on physics. So thank you, students.